Okay, good morning everyone. This is Stuart Finn from the University of Queensland and Earth Observation Australia. Welcome to our whole of community webinar series for May. Hope everybody's doing well this morning. Just before we start, I'd like to acknowledge the traditional owners of the lands and waters on which we meet, so elders past and present, and their new and emerging leaders as well. Just in terms of a bit of logistics before we start, we are recording this just so everybody's aware of that. And we would ask that everyone keeps their microphones on mute and their cameras off unless you're one of the presenters during the presentation. All of the material that you see today will be available on the Earth Observation Australia website, and I would like to acknowledge Larissa Marfan for putting all of these materials together and making sure they get out to everybody as well. So Larissa, could we get the slides back up on the screen just to begin with, please? Thanks. So just while we're getting the slides back up on the screen, at the moment, I'll just note that we do have a slightly larger and more diverse group than normal online today. So welcome everybody. For those of you that don't know, Earth Observation Australia is a not-for-profit incorporated body which provides coordination and collaboration services across research industry, government, NGOs, in Australia for people who collect and use Earth observation data, whether it's from satellites, aircraft or drone, to monitor and manage the environment. So we're funded through a range of different sources, but what we're about is enabling people to share knowledge and learn from one another, and that's really what we're going to be doing today, but having a look at coral reefs. So I'll come back to that in a minute. Before we go into today's topic, I did also want to point everyone's attention to the banner at the bottom of the screen. Our inaugural national forum, like a new type of conference, which is not a usual conference, has been shifted to August 2021. So if you want to learn more about using Earth observation, whether you're from sort of education, research, small industry, large industry, state government, local government, national government, this will be a really excellent event to come along to. We'll have a lot of really interesting and different sessions that aren't just your normal sit down and listen type things as well. So if you want more information about that, it'll be on the Earth Observation Australia website. Right, the next slide please, Larissa. Okay, so here's the program today. We're fortunate enough today to have the lead scientists for what has become the main sort of global coral reef mapping and hopefully monitoring activity to talk about how the project was started, what problems they've had to overcome, and how they're actually going to use this to move forward in future. It's of interest to Earth Observation Australia because this is a really good example of research being done at sort of local site levels, linked in with ecology and resource management, which they got it working at one scale and they've had to move out to doing it globally. So Dr. Chris Rolfsamer, Dr. Mitch Lyons and Dr. Emma Kennedy will be presenting on that today. I'm fortunate enough to be involved with the team as well, but I'll be doing more questions and directing things today, and I'll let Chris and Mitch and Emma do the sort of hard work on things. So you can see the outline there. I'm just going to finish the introduction by introducing the people who will be presenting or talking today, and then I'm going to hand it over to Chris to present. So just to begin with, everybody who's on this team is based at the University of Queensland. Chris has led the development of remote sensing and marine Earth observation applications at UQ since the early 2000s. He's initially worked on seagrasses and then corals. He does have a surveying background as well, and spends a huge amount of time in the field linking, what they can see and measure there to what you see in the actual imagery. Chris has been able to put together a large and very appropriate team to build this global mapping capability, which you'll hear about today, and why it's necessarily a multidisciplinary approach. The people joining Chris on the panel, Dr. Mitch Lyons and Dr. Emma Kennedy, who got the cameras on now as well. So Mitch's background is he also did a PhD, but more looking at seagrass dynamics from remote sensing, but has since moved on to doing a whole range of other applications, from linking field measurements to high resolution mapping to online mapping over continental to global scales, and also works across UNSW as well as UQ. And our last member of the team, but also a really critical member, is Dr. Emma Kennedy. Emma brings a large number of years of field experience working in reef ecology and management. The position she was working in before this was a similar project to ours called 50 Reefs, which looked at a large number of reefs globally. And one of the reasons that we have Emma on the team is to make sure that what we're doing is linked effectively to ecology and management applications. So I'll stop talking now, and I'll hand over to Chris for his presentation. And after that, we'll take questions. Those questions can be in the chat window and you can type them as we're going, or you can bring them up when we have the discussion as well. So I'll be prompting the presenters with some questions, but also take questions from the audience as well. And the links to the Research Centre and the project were also on the screen you saw before. So I'll hand it over to Chris and let him share his screen. Thanks, Chris. Yep, all good.
Good morning, everybody. Thanks, Stuart, for the introduction, and thanks, everybody.
So, Chris, we can't hear you at the moment.
Oh. Can you hear me now?
Yes.
Okay.
Cool. Good. Thank you.
So, good morning, everybody, and thanks, Stuart, for the introduction for this project and the team members. And as you notice, I put a whole list of other people on here as well that are part of the project. So I will go give an introduction and an overview of this whole project. If there's any questions regarding the overall, then that's ideally go to me. Other questions in the more technical bits can go to, especially the Google Earth engine, can go to Mitch. And any conservation and ecology question relating to how the maps are used and the classification scheme can go to Emma. So keep that in mind so that you can address the question as well. Please ask questions, and please feel free to email me afterwards or one of us afterwards if needed. So yeah, coral reef habitat mapping from the Great Barrier Reef to reefs globally. Now, before we go there, it's always good to just stand still and understand what coral reefs are and why they're important. Well, what a lot of people don't realize is that 1% of the ocean surface is actually a coral reef. And the other part is that 25% of all marine species depend on these coral reefs. So even though that's a small area, they are significant of importance if you look at the whole Earth's surface. Now, reefs are one of the most endangered species on Earth's surface, and hence we need to take care of them as well. Next to that, coral reefs in generally provide enormous service to the community globally, but specifically locally. And locally, thinking of, for instance, the local fishermen where living around coral reefs, they are mostly located between the 22 latitudes. And there you find people using these reefs on a daily basis to get food for their families or to sell to other families. Next to that, these reefs are protected by, these reefs play an important role in protecting the land behind it. And this is a classic image of a reef crest here in front, open ocean in the middle of the Pacific and beautiful islands on the back. And people can safely be on these islands because of these barriers. Now, the impact on these barriers is through storms and so on is enormous and will reduce those reefs as well, and that can have significant damage in flooding to towns and so on. Sadly, we know that the coral reefs are in crisis, and you should, even with the whole COVID crisis at the moment, most of you should have heard about that. Also this year, the Great Barrier Reef had a significant bleaching event throughout the whole reef system. Although the corals maybe look nice when they're white and all these pink colors, they're actually on life support, and they could die or recover, but sadly most of them die. So yeah, that's not a good news, and that's coral bleaching is definitely a result of global warming. So if we look at these reefs and the satellite imagery of a reef, then we know that this kind of information returning into habitat maps can be used by management and researchers to better understand and also manage this environment and monitor these environments. So just for those who are not aware, when we talk about the benthic community, we basically talk about the environment where we look at the algae, the composition was on the ground, algae, rock, rubble, sand, seagrass, and corals that make up this environment. Each of these different areas on a reef will have a different composition, and that can be characterized by the different geomorphic zones. Each zone has its own importance, and knowing where these zones are will help managers to see also what area they have to focus on of importance. You could say it simply as that the lagoonal areas may be more a rural area, where the crest and the slope is like your city, where most of the business is happening and lots of activity is. So knowing those two areas gives us a better understanding of how to monitor and conserve these regions. Now, where coral likes to grow is important to know. It's not only that you can see it in the picture, but in the satellite image, but also understanding that it likes light, it likes certain temperature, it likes a certain water chemistry, it likes hard bottom and wave action. And the wave action, for instance, is a classic example that we can use to help predict where massive plate or branching corals grow, or a mixed community in this environment. And then, of course, there's the understanding of what's happening from a remote sensing perspective. Now, we all know that these environments above water is reflection, scattering, absorption, and transmission, but not everybody is maybe aware that once we get underwater, we have that as well, but in a different level. And as a result, we cannot, simply said, I always say to a manager or a scientist, if you're rowing with your boat over this environment and you can't see the bottom, then there's a big chance the remote sensing can't help you also, or at least the optical remote sensing. The colors are changing, the light reflected is changing, and it's depending also on the composition of the water column, how much it's changing. Now, if it's all standing still, that would be easy, but it's moving. So the tides take care that the depth is changing, currents take care that the water column gets mixed, and the water column properties changes, and waves take care that the surface of the reef changes, of the water changes as well. And as a result of all these changes, we're challenged that we really like to get the best images possible, of course, with clear water on a no wind condition and with a low tide, because then you have can penetrate the deepest with your light. So yeah, we need to understand this and consider these challenges. Next to that, of course, everybody knows that clouds are challenging, but specifically on coral reefs that are in the tropical environments, there are actually a lot of clouds. So getting cloud-free imagery is actually not so easy for tropical environments where the coral reefs are. So we try to get an understanding of these reefs, and over the years we developed this approach where we actually collect georeference photo quadrats of the seabed. We do that on snorkel or scuba, and we can do it with drones as well if needed. But these are simply methods which are just a standard camera and a standard GPS. The photos are georeferenced because of the timestamp and can be plotted on the satellite image. The photos are analyzed automatically using a program called CoralNet, where we basically do some level of, let's say 3% of our photos are used for training, 3 to 10%, and the rest is automatically analyzed. And the cool thing of that is that we actually can reanalyze them if we want other categories to be included, because we, in a later stage, we see an importance in the specific category. So it's very powerful. So for instance, we have a time series of Heron Island of photos, every year 3,000 photos, and just recently they're all been reanalyzed over for a 20-year period. Now, with this detailed field data, you can create really good and detailed maps. And here's an example of Heron Reef with a lot of different details in classes as well. But that requires a lot of field and processing intensive for one reef. So the question is then, of course, so how do you do it for many reefs? Because how much I like diving and go underwater, I do prefer to, how do you call it, to map these reef systems as much as possible and to stay home as well, now and then. Now, to understand this reef system, we have to also look at the scales we're looking at. And for those of you being involved with the national classification work for aquatic system, some of that work done with Mike Ronan is integrated in here, and it's closely following the wetland protocols of categories as well, where we're looking at these different scales, where reef systems represent a couple of reefs, like here the Capricorn Bunker Group. A reef type can be fringing reef, lagoonal reef, or barrier reef, or atoll reefs. Then we can have different geomorphic zones on each reef, where a reef slope, crest, outer and inner reeflet, and lagoon. And then we can have different benthic habitats with different compositions, as you can see on the right. So these, all these different maps are possible for these different areas. Now, if you put it back to the Great Barrier Reef, the Great Barrier Reef is actually, has no detailed habitat map. This is Heron Island again, and this is the highest level of detail that is present for every single reef on the Great Barrier Reef. Knowing that it's 3,000 reefs long, 3,000 reefs in total and 2,300 kilometers long, it's not amazing that it's a hard area to map. Take it in contrast, the land part of Queensland is mapped almost on a monthly basis for its habitat. For the Great Barrier Reef, that's not existing at this stage. There is, of course, a satellite cover, and that can be Landsat imagery with its characteristic Sentinel-2 imagery, or Planet Dove. And the different imagery have different pixel size, but also different revisit times. So to get a global mosaic of these images can be challenging, or get a mosaic over the whole of the Great Barrier Reef can be challenging, keeping in mind what I said previously about low tide, winds, and cloud cover. With this information in mind, and the amount of work we did initially on Heron Reef and other reefs locally or overseas, we were asked to aim and develop an approach to map large reef systems to geomorphic zonation and benthic composition level. We focused there, of course, we used our knowledge from Heron to initially go to the Capricorn Bunker Group and the Cairns region, funded through the Great Barrier Reef Foundation. That resulted in 2018 that we were asked to map the whole Great Barrier Reef, and we are still on track to finish it off by January 2021 to have our first version of the map. But as you will see throughout the presentation, it can ongoingly change. It's through the processes and techniques we apply. As a result of this work, it triggered that we were asked by Vulcan Philanthropic to map all the reefs globally. And yes, that's a bit more reefs to deal with. At this stage, we estimate that the number of reefs is 231,000. Now, how do we do this all? So, initial mapping approaches of reefs were based on satellite imagery and field data. Nothing more. The work we've been doing is actually integrating our knowledge about the reef, geomorphic and benthic, the impacts that take place, with physical attributes such as water depth, wave climate, and slope angle. So it's not depending anymore on the color of the spectral characteristics of the pixel, but also on other parameters. From the satellite imagery, currently all kinds of approaches have been developed over time to derive water depth. You can split them in two kind of levels: the physics-based inversion, which results in absolute water depth, or in our case, and then the ratio-based derivation that resulted in relative water depth, where the first one is more complex but results in higher accuracy, and the second one is more basic and lower accuracy. But there are different methods now that are suitable to be operational. If we have wind data, then we actually can use the wind and the water depth data to look at wave characteristics, such as wave height. With depth and fetch, we actually, where fetch is the distance over which winds can create waves, basically, we can make very detailed wave data with various parameters. With fetch only, we can still do wave height, but or wave energy, but it's less detailed. So that are input data sets. Then we get to how to create these maps. So initially we focused on object-based analysis only, where you basically segment an image in different parts and use the different input parameters, not only the image, but also the wave data, the slope and water depth, and our nearest neighborhood relationships, so the relationships between the different classes. So for instance, you expect next to a reef crest a slope, because that's where the reef dives into deep water. And we can use that in object-based analysis. So Emma has been working on a classification scheme that we're now implementing for our work. And that closely follows the process we've done, but also is in line to a certain extent with existing classification schemes. For instance, if you have water depth over a reef, like here a cross-section of Heron Reef, then you could label different areas partly already just purely based on their depth, if you have good water depth. And here's an example. In blue you see Cassie hyperspectral derived depth, and in the red Landsat derived depth. So it's two extremes kind of thing, but both show roughly some of these characteristics. So that information we can use to create these rules, that you look at for instance, consolidation, the depth, the horizontal, if it's flat or sloping, windward part, if it's wave, a lot of wave energy or less, or the neighborhood relationships. We can use that as well in the coral. Once we have a geomorphic, we can use it as well to help creating a benthic map. And then with ecological map modeling, using those previous maps and the wave data, we actually can, and field data, we can create, we can model the massive branching and plate coral throughout the reef system. However, we need the very high level of detailed wave data and field data to be able to do it. So that's nice for one reef, and here we showed it for 20 reefs, or roughly in the Capricorn bunker group, where every reef has been treated on the same way. So every went through the same process. That's nice, but that's only 20 reefs. So we started on BARC over the last 2 years on starting to work on the Great Barrier Reef, on looking at 3,000 reefs. So we collected field data at specific reefs we selected that are characteristic, and did the several activities, the main ones being the snorkel and dive transects to get those photos. That resulted that now we have over 100 reefs visited in that time period, and we have a large amount of detailed photos of the Great Barrier Reefs that we can use for our analysis. As a result of that, we first initially focused on applying the rule sets to a small area, and then apply it to another area, improving it, do it for another area, and then said, okay, that works, let's now apply it to every single reef. And that process resulted, while going, into a geomorphic map, but also a benthic and a coral type, a predicted coral type map, which is the first on its kind for the Great Barrier Reef at that, for that part of the Great Barrier Reef at that level. And then we came up, okay, now we need to see how we can do it for the whole reef. For the whole reef, we use the same kind of approach. We use Sentinel-2 surface reflectance data and physics-based derived depth. We use the depth and fetch-based wave modeling to get 19 different wave parameters. And we can use the very detailed field data to help inform the benthic, but also the coral type mapping, especially the coral type mapping, the detailed field data is required. The reef is too big, so to develop this into ecognition, we realized that doesn't work, and that's where specifically the work from Mitch Lyons came in, where he basically translated part of the work done on the GBR into the Google Earth engine. That resulted into 4 models, and he can talk way better about it than I do, where in the first module the data is ingested and then segmented so that we still follow that object-based approach. Then a random forest classifier is applied to it to basically give the first classification, the raw classification, what we call it. And then we use object-based analysis to do the cleanup phase. And then with some part of the reference data, we do an accuracy and confidence level map as well. So that every map created, or every area created, can have accuracy as well. The code is all available in the online, and you can email Mitch about it. It's not a secret. Anybody can work with it if they want. And as a result, we actually can now look at maps of the whole Great Barrier Reef, at least at geomorphic level. And I'll see if this works. Let's see. No, it's not working. So I will do that later. So basically here you see a first example of all the reefs of the Great Barrier Reef. From the far north to Lady Elliot in the far south, every single reef has now a geomorphic zone. We're constantly updating it with new data or new improved methods. And it's a live kind of situation. We trying to communicate to everybody that you could say there's not a final map because there's a versioning of the maps. So Paul Allen, the late Paul Allen, found out, of his team found out about the work we are doing. And he approached Stuart and myself, or his team approached Stuart and myself, and asked if we were interested to work on a more exciting and even bigger project, and that's the global Allen Coral Atlas. If some of you maybe know that there are many reefs on the Earth's surface that are mapped, but one of the main challenges of it is that the maps that are available for those areas are static, they're not updated regularly, they are not mapped for each area at the same level of detail, and some reefs are not mapped. And here's just some examples of different reefs, mostly at the same level of scale. That's a result of that the UNEP layer that currently represented those yellow lines is a result of anybody sending the best maps to UNEP, and then UNEP puts it together. So yeah, the question is, can we improve it to do it on a global scale? So that got us a team together with Planet, Arizona State University, University of Queensland, Vulcan, and National Geographic, where Planet provides the satellite imagery, Arizona State University pre-processing, University of Queensland the calibration, validation, and habitat mapping, and Vulcan takes care the pipeline gets interfaced online. And then National Geographic is communicating to the wider audience. We divide, to do this mapping, we divide the world into mapping regions, characterized by the ecology, but also the type of reefs in those areas. And for every mapping region, we try to get enormous amount of field data through desktop studies. That's led by Kat Markey and her team, to get existing ecological field data and existing maps. In some parts, we train people up to use our photo transects and have teams going globally, going to different areas in the world to get photo transects to provide us with even more detail. This all gets into the Global Earth engine, but now we use a low-tide DOF mosaic, which is the uniqueness of DOF, that we can really get low-tide images. We get a composite of different depth at ratio-based approach from Sentinel, Landsat, and DOF. We get fetch-based, so not so high level of quality, but still useful. And then we get more field data and existing, and we rely more on, mostly on existing field data and maps. Same principles. Till now, we've done small areas that you see in the little round circles. And we actually just finished in the last 2-3 months some really big areas. So the Southwest Pacific, the Micronesia, and North Caribbean. Currently, we're working on East Africa, and the next ones up are the Andaman Sea and the Hawaiian Islands and the Southwest Indian Oceans. All the data will go online onto the Allen Coral Atlas, and anybody get access to it. And they're currently working on that. Not only can they get access to viewing it, but also download the benthic maps and the geomorphic maps. The methods applied are based on a global basis. So obviously, I'll see in the HERM maps changes, a higher level of detail of what I've done in the past, but in the global map created for the whole of the GBR, you won't see the same level of detail. So it depends on how much effort you put in it, of course. And here we try to take care that we have continuous maps for every single reef, using comparable methods. Now, that's not all done by myself, that's done by a whole team of people within UQ. They are specialized in remote sensing, obviously, in GIS, in coding, in Google Earth Engine, in Python, in R, but they also specialized in field data collection, in ecology, in coral reef biology. So there's a whole group of people coming together to work on this project. Stuart, Emma, Mitch, and myself are now here to answer any questions for you. The project itself is aimed to have by 2021 most of the reefs mapped in the world. And like I said, anybody can go on the Allen Coral Atlas, and the website was given to see some examples for that. Thank you.
Great. Thanks very much, Chris. And just before I turn back over to questions, I just wanted to show something briefly. One of the things that we've struggled with is showing people the extent of this, that it's global, but it's a really high level of detail. And just to give people an example, I mean, you're looking at the atlas on the screen now, and that's basically a mosaic of Planet Dove images. And as Chris pointed out, we're able to get image mosaics at specific tidal stages that are cloud-free. And for those of you that have done satellite image mapping, trying to get cloud-free imagery at specific times would understand how difficult that is. But you can, I guess with the atlas, you can zoom in anywhere. You can look at the benthic categories. So all the imagery is already in the atlas, and you can go down to that really high level of detail. And the mapped areas which are in there, once that sort of wakes up a little bit, I mean, you get down to that level of detail that Chris was showing you. So, we are talking about millions of square kilometres mapped at an extremely high resolution in a repeatable way. So I'll just stop there, and I know there's some questions coming in, but what I did want to do just to set some context to those questions, Emma, could I just get you to briefly explain how this is different to what's been done previously, please?
Yeah, of course. So people have been trying to create global maps of reefs for a really long time, and actually Darwin was the first person that had a go at this in the 1840s, and he had like a pretty good stab at mapping like a lot of the world's fringing reefs and atolls. It's like, if you ever get the chance to look up that map, it's pretty fun. And then for a really long time, we were pretty slow mapping reefs, and it was only like advent of, I guess, computer technology in the sort of 90s and satellite technology in the 70s, the way people were able to start digitizing like old charts and people's detailed small habitat maps, and putting them all together to try and get a more detailed picture of how reefs were mapped. And so the Millennium Reef Mapping Project created this global data layer, and that had a lot of Landsat imagery in it, but it didn't, mostly it's outlines of reefs, and it hasn't been mapped in a really, really consistent way, as Chris was saying as well. So I think the thing that's exciting here is the big scale that we're able to map at, the new level of detail, which of course isn't as detailed as if you were mapping an individual reef and had a lot of time to do that. And then I guess thirdly, the fact that it's been done in a really consistent way. So it's really cool to be able to do these big kind of regional comparisons and understand the distribution globally of reefs and how that compares.
Thanks, Emma. So just taking that last bit a bit further. So Mitch, in terms of applying this sort of approach globally, if there wasn't a large online data store and processing capability, would this even be possible?
Yeah, that's a good question. I mean, you can do things like this by distributing it on high performance computers and kind of farming it out and bringing it back. But these types of projects are, they're iterative, and you need lots of feedback kind of constantly. And doing that outside of an environment, something like Earth Engine or other various data cube style things, is very difficult to do, because you don't get that feedback. So like when I'm making a map or doing something like that, it's really difficult sometimes to know whether it's right or wrong, or whether distribution is right or wrong, or even how it feels. And it's really easy to get feedback when you have kind of this mechanism where you can show lots of people. I think that's one of the unique things about this project, is that I guess the range of people that are giving us feedback constantly, and it being an iterative process rather than just like, here's a map that we farmed out to a HPC and then here's what it is. So yeah, I mean, you can do these things like that, but it's very difficult. And at that kind of scale, these types of systems are ideal.
Yeah, cool. Thanks, Mitch. That last point about feeding other information in fits into the question that Andrew Skidmore's put in the chat there. I might go to Mitch and Chris on that particular question. One of the points Mitch mentioned there is the system that's being used is having input from people on the ground around the world all the time to help it be matched to local conditions, but there's a lot of other attention that's paid to attempting to validate this as well. And as you appreciate, it is global. It's across a range of different areas. So it's a challenge. So Chris, did you want to comment on the what accuracy are you obtaining, and how is the verification undertaken?
So the verification, how it's undertaken, is that basically we're getting some of our own field data, which is limited in the sense of looking at the whole Earth surface of a reef extent, and then we get field data from others as well. And that is mostly existing data, so it could be partly out of date, obviously. We use those different data sets to go into an approach where we start to look at the individual images within a region, or sorry, a set of images within a region that characterize certain reef systems. And we basically create what we call a reference set of data. That reference set is then used to, I say, split into calibration and validation. And calibration set will be used to feed into the random forest classifier, and the validation set is to do an accuracy assessment. So obviously it's all as good as the reference data is that goes in. And obviously the accuracy is basically says how good the reference set is, but it doesn't, and it should give a representation of the whole region. Now the accuracies that we get, I would roughly say they are between 50 and 80, 90% range, depending a bit on the region where we are mapping. On average, probably more around 75. Stuart and Mitch and myself have always a bit the feeling that we have to teach the community to not only look at accuracy, but also look at other values, because the overall accuracy on it is just one number for this whole map. So the other thing we're working on is getting confidence layers that basically provide, that uses the classification output, the probability of the random forest, if the presence of any artifacts, because all the maps all the imagery going in are checked on artifacts, are used to basically come up with the confidence level, and the quality of the reference sampling is going in as well. That results in a confidence level map, which basically gives a better idea of how the confidence is in the map. Anything to add, Mitch?
No, not really. Just in the sense that, yeah, like when you look at these such large scales, looking at individual numbers is often doesn't make a lot of sense. So yeah, we're trying best as we can to produce these kind of spatially variable accuracy layers and confidence layers and stuff to help people interpret. And as Chris said, it's as much about education as it is about giving individual numbers to people.
So one of the things that we do come across with the feedback is that, of course, you know your own backyard the best, and when you look in your own backyard and you see that the pixels are good, then you're happy. If they're not so good, they're not. And then we get feedback and we try to incorporate it. But what we're trying to do as a team is to split that feedback into two kinds of components. One are feedback that are returning, in the sense they have same kind of characteristics, and we need to see if we can adjust the code of the classifier and the cleanup rules for it. And then the other feedback is basically like, yeah, that's how far we can go. And people can download the maps and update it themselves in their own use if they know their area specifically. And a lot of NGOs don't have that level of detail for all their reefs already.
I think the other important point of that is the field data that our teams are collecting are those geo-referenced photo transects, which Chris showed you in the presentation before. So that's it's an ongoing challenge, and it's a communications challenge as well as I think anyone that works with image-based maps that are being updated. Just going back over some of the other questions. Solomon's question about the presentation, and this is for everyone. The webinar is recorded, and I just posted the link where you can access those. The data that's actually behind the maps, the planet data, and then the maps themselves. So the maps themselves you will be able to download off the Allen Coral Atlas site. And I'm going to have to ask Mitch or Chris or Emma about the actual Planet Dove layer that's downloadable.
So the bottom reflectance products can be will be able to download, and the pretty picture mosaic can be downloaded, will be able to be downloaded as well, or downloaded the web links people can get to the web service. The raw imagery not, and I think the surface reflectance data also not.
Okay, so at a minimum the data sets are downloadable in terms of the benthic and geomorphic layers. The imagery I think should be there actually soon. Some of the other questions, so Steve Sagar's,
the depth data will be accessible for people as well.
Yeah, all right. Thanks,
and the wave data also.
And the wave, yes, that's wave climate data. Steve Sagar's questions, there is a parallel to us, the Arizona State University group, Greg Asner's group, is building a monitoring change detection system, which is close to being operational at the moment. And that is looking at sort of sub-monthly scale changes in planet imagery globally. In terms of what happens after this is the first stage is done. This is ideally a sustained project and resource. It's being built so people can continue to submit information, and ideally that we continue to improve the algorithms and the maps. Question from Arna Nakad, which I will put to the whole team because it's a really important question. And this work sometimes does feel like discovery. It was, did you find any new reefs?
Definitely.
Yes.
This is not, so let me say it this way. We definitely found reefs that have not been mapped before at all, or reefs that were mapped but just partly mapped. And so there was not a lot of level of detail present. So definitely we find new reefs. But obviously anybody listening to my talk very well should also pick up that, yeah, if you can't see the reef from space, we don't map it. So in some areas there are maybe turbid reefs present, and you can see on the existing maps already that there's not a detailed outline, it's more an artificial outline created for those reefs. So it's clear that others couldn't map them also, but they use field data to highlight them. And yeah, we won't, anything we can't see, we won't map them. The reefs will be mapped for benthic up to 10 meters and for geomorphic up to 20 meters. And that's consistent globally with the purpose to be clear, like, yeah, even if the water is clearer, we maybe can map deeper, but we want to have a consistent layer so that it's comparable.
Thanks very much, Chris. I mean, there's been some good discussion on the chat with Emma and Mitch answering some of the trickier questions. Thanks, Emma. for that. There were some other questions about Sentinel-1 and 2. Sentinel-1, when we haven't looked at for land and water boundaries. Sentinel-2, as Mitch said, we are using that quite extensively for a whole range of different applications. I do also want to point out that using something like Earth Engine, it's very easy to bring in those large-scale global data sets as well. So I think we've dealt with a lot of the questions. Chris, just to clarify, that point you made before about 10 or 20 metres, that was the depth that they go down to, right? Because there was a question about the resolution of the products.
So the resolution of the products is basically, you could say that, of course, the smallest pixel size we're working with is 5 meters, but anybody using remote sensing knows that you probably scale it up to, to another level of detail. But we basically advise people to use the right scale to zoom into areas based on our classification scheme. So for geomorphic, it wouldn't make sense to go into look at the individual 5-meter pixel, where with benthic you maybe would look to a smaller area, but not specifically a 5-meter pixel. And with depth, it's a product of Landsat, Sentinel, and DOF. So the biggest pixel is basically the most common depth we will be using is Sentinel because it provides us a better quality. So that's around 10 meters, but yes, Landsat is of course 30 meters.
Right, I'm just conscious of time. I did want to try and finish off with a question for Emma to comment on, which is some of the questions that we've had have been about the future of reefs. Chris has commented on it in his talk as well. You know, why are detailed maps like this, I guess, so important or critical, and you know, why haven't they been done before?
I think the thing that's exciting about this project is there's so many different applications for the maps, and the more people we talk to and reach out to, the more and more people have bright ideas of what they might do with some of this data. But just in terms of resource allocation, there's really good geopolitical reasons why we might want to be able to count and have a good idea of where these really vulnerable ecosystems are, where it's located. Like traditionally, we always say Australia has 10% of the world's reefs, but that might not be right, and those numbers might really change quite soon when our mapping's finishing, and that's becoming increasingly important when we're negotiating over carbon emissions and things like that. And that kind of information is really useful for organizations like the IUCN Red List, whose assessments of species extinction risk depends on global habitat extent. So there's lots of conservation applications as well. So placing marine protected areas and planning. And there's actually a really nice example of a reef that Chris mapped at the beginning in Sri Lanka, where they used those maps to create a brand new marine protected area based on the mapping that the team had done, which was really exciting to see. And then disturbance monitoring as well. Chris mentioned in his talk how looking at climate change impacts and looking at those through time on reefs. But even, I think I mentioned it in the chat, while we've been mapping, we've been able to see things like recent destruction of reef flats in PNG, where people have created kind of blown up bits of reef to make deep water boat access. So it's for kind of tracking disturbance over time. And then of course for modeling, like big scale models. So people in Australia are probably familiar with Reefs, which is a kind of set of biogeochemical models, and having better benthic habitat information going into those models means that the outputs get, the resolution of the outputs get better. Things like connectivity modeling on the Great Barrier Reef and planning when everything's changing so much is really important too. And we've even, we shouldn't talk about these maps and navigation, but we've even found when we're working in the field, some of the boat operators that we've been working with right up in the far north, things are mapped so badly out there. They've been really excited to just look at the baseline satellite imagery and be able to see the reefs and work out where good anchorages are. And that kind of information hasn't always been available before as well. And I think the final thing is it's just really fun. There's a lot of fun that we can have with these maps and ask big questions like how much coral is there in the world, or space for corals to grow, and updating estimates of that as well. Those kind of questions are pretty fun.
Great. Thanks very much, Emma. All right, well, we might close things off there. And just to close that off, I do want to thank Chris and Mitch and Emma in particular for doing this at the last minute, because we had, I guess, a cancellation, let's put it that way. So I appreciate them doing this at last minute, and it is a little bit rushed, but it was excellent as usual. But I think this does show one of the real strengths of Earth observation in terms of being able to build new technologies and capabilities, but having it being able to be directly used in government and other activities in Australia and around the world, but also the fact that it requires cooperation across a range of different discipline areas. And in doing this, we can, this process has broken and done things at Planet and Google that they wouldn't have done without us pushing them to do it. So it's been a great process. So cool. So thanks everyone again today. And again, for everyone who's attended, thanks for your time today. The slides and audio will be up on the website a little bit later on. And Marissa's also just posted in the chat the detail there. So, and thanks to Larissa for setting things up. So thanks everybody for your time today, and we'll call it time on that. So thanks everyone, and we'll see you soon.
See you soon. Thanks.
See ya.
Thank you.